Professor Anna Delin, Royal Institute of Technology, will deep dive into the possibility with new materials sourced from urban flows, making sure that we can reuse them over and over again. She's also leading the school of WISE, the future of development we will see now. Anna Delin, you are professor at KTH and head of the research school WISE. Looking forward to listen to you.
Thank you. So thanks for having me. It's been a great workshop so far, I think. I learned a lot, also about new materials. I'm here to present a large research project that recently started in Sweden. It's called Material Science Initiative for Sustainability. And it's funded by the Wallenberg, one of the Wallenberg foundations. So I'll just start with a general introduction, something that you all are very aware of, which is that materials are extremely important and is really the basis for our advanced society and the high quality of life that we are enjoying. So this is a picture of the materials sector in Sweden. There's a lot of steel, for instance, and what is that? That's porous materials. You can see that it's increasing. The material sector is increasing, and it's an over 300 billion Swedish crown industry. The global use of resources is increasing. We heard that before. It's about 100 billion metric tons, and it's increasing quickly. So this is what we're dealing with. And all this use gives up lots of new resources like this, but they're mixed up. The atoms are in the wrong place here. So a resource is something that something that we can use where the atoms are in the right place. But if we mix them up like this on a dump, they're in the wrong place. And then it costs us a lot of work to put them in the right place and make it into a new resource. Here, I have some numbers. So the primary production of materials accounts for 25% of all global greenhouse emissions. This is our job with taking out material from the earth and trying to put them in the right place so that we can use them for buildings, for instance. And just metals exploits about 8% of the global energy use. So how can fundamental material science contribute to solving these problems? We've heard today that regulations and standards are really important, and actually I think that's where we really have to work. But fundamental material science is also what has actually created are all the possibilities and all the fantastic things that we enjoy today, but has also, of course, contributed to these problems. Like, yeah, I don't need to mention all the horrible materials that we have around. So a starting point could be to take the Sustainable Development Goals from the United Nations and just write out how material science could contribute. So here we have number 11 up here, and it's buildings. And here we have written settlements built up from materials that are safe, resilient, and sustainable. And of course also recyclable. And in fact, of course, this question has been important in material science for many years, but not funded in this organized way that we now have with WISE. And material science is already making an impact. So here I have a couple of examples. This is the energy sector, so energy from renewable sources. Here we have the happy development that wind and solar produce more of the European Union electricity than fossil fuels for the first time. It's really going in the right direction. Very happy about that. And this graph shows us that the share of energy from renewable resources is, in many, many countries, is dominated by renewable resources. This is fossil-free steel. I'm sure you heard about it. What I show here is sponge iron, and it's made in an old new fashion, where you take iron ore and reduce it directly using hydrogen. This technique, a similar technique, has been used for a long time when you can't use coal because you don't have coal, and you can use natural gas. And that's a mixture of hydrogen gas and carbon monoxide, and you can use sponge iron. But there's a new, these are industrial projects where they develop this process so that it becomes competitive at a business level. So we have hybrid, we have H2 green steel and green iron. I'm sure there are many more similar projects. This is really driven from, I know, at least the car industry, where they want to sell, the customers really want to buy a product, a car, that's fossil-free. And that means that it runs on electricity, but also that the steel, the material that the car is made of, is produced in a way that doesn't contribute to carbon emissions. So, and this is where WISE comes in, where we, with fundamental science, we try to produce new materials and also how to make them more circular. So our vision is a sustainable future through material science, and we want to perform material science research at the international forefront to empower sustainable technologies with positive impact on society, and to train future leaders in society, industry, and academia. And maybe here, this is interesting for you. So there's a lot of young people coming in, PhD students, postdocs. They get training in material science, but also sustainability. And we hope that they will be very employable for you in the future. Now I'll tell you a little bit about the organization of the WISE project. So we have 4 thematic areas, because you can't do everything. It's very wide already. Energy, climate, circularity, and discovery, in short. And you have the more complete formulations there on the right. And then these thematic areas are addressed using a number of, let's say, research perspectives or methods. So we can do design modeling, synthesis and processing, structures, properties, and performance. And of course, lots of materials characterization. And for this, you need a lot of advanced research infrastructure, which is an important part of the financing of WISE, that advanced infrastructure. And these are the participating universities. So you see it's from the south to the north in Sweden: Chalmers, KTH, Linköping, Lund, Stockholm University, Uppsala, and Luleå. And then we have affiliated groups in some other universities as well. Here are the main program components. We fund new faculty. This is internationally renowned young scientists that we try to recruit to Sweden and have them stay here. We have a guest professor program. We have lots of PhD students and postdocs. You see, the graduate school will have almost 400 participants. We have the research and technology platforms. That's the research infrastructure. And it's sorely needed. It has been an underfinanced part of Sweden's research for a long time. Then we have something that you might think that could be interesting for you. It's called VIRAS, Industry Research Arenas, and these are envisaged as physical spaces where researchers from academia and industry can collaborate in a very informal way, and you can do open-ended experiments. This can be, this depends on the vision of the people involved, what this becomes. So we started in 2022, but really this year we started fully, and will run for more than 10 years, which is great because you need long-term funding for fundamental science to be able to actually focus on important questions. And the budget is around 3 billion Swedish crowns, and very generously funded by the Knut and Alice Wallenberg Foundation. Am I already over my time?
3 minutes.
3 minutes. Examples. Now I come to the really interesting part. So I collected some examples from that you could use for building. It's much wider than this, but these are just some examples. So this is my first example. It's transparent solar cells that you could use to put on glass, even glass walls, so you wouldn't see the solar cells. And the reason one can do this is that the solar spectrum has lots of light in the beyond the visible part, so you can collect that. And if you can have those solar cells over a wide area, you can actually make quite a lot of solar energy, electricity, and it's based on very precise manipulation of nanowires. My next example is also glass. So here they add calcium and aluminum, not just silicon oxide, to make ultra hard and crack resistant, very thin glass, and also how to recycle these in a good way. This is one application is, of course, architectural glass. We want lightweight structures because then the supporting structures of a building can be made lighter. My third example is also lightweight structures. So they do lightweight and strong structures using additive manufacturing and 3D printing, and also how to recycle these easily. Fourth example is insulation materials made from various waste streams, agriculture residues, textile waste, and that's something we need in Sweden to reduce the heating costs, of course. This is my next to last example, and it's a lot of fun. We don't want mold in our houses. Nobody likes mold. But in fact, you can make insulation materials from fungus. What you use is the mycelium, the stuff that's underground. This is a new old technology because in Romania they make something called fake leather using mycelium. And what you can do is if you put the mycelium, you give it food and you have it in a form, it can grow in the form you want it. And once you don't want to use it anymore, it composes very easily. It's just compost. So this is actually an insulation material that they have done in this way. And finally, we have concrete, the big bad boy of construction materials. What people are doing here is to make it more durable, crack resistant by adding fiber. This is also known technology, but they want to optimize it, and they're looking at different applications. And the circularity aspect here is the smallest of the circles that we saw in your presentation, which is that we want things to live for a long time. As long as the atoms are in the right place and we can use them, then we're happy. We don't need to use any energy or work to move them around. And thanks for listening.
So, Raul, please come forward as well. I know that we're running late, but this is a moment we can't miss. So we need to have a questions and answer session. So tell the lunch people that we're running late a couple of minutes. First, 2022, it started, you said. But these innovations are, I guess, been before, or?
Yes, these are examples. Since we just started, I had to take examples of what the research groups are focusing on, and the projects they are working on are in this direction.
So we'd love to see the examples from your 186 plus 186.
In 10 years' time, yeah.
Exactly.
Yeah.
So before I go to Raul, are there any things that you've seen today that you see, this I'd like to know more about? From today, are there any examples that we like, this I would like to understand how we can integrate in our way, in our research at KTH? Are there anything we discussed or examples you've seen here?
Yeah, it's the perspective of organization, that this is somehow material science is quite nearsighted. You try to make a better battery, a better solar cell. How can we recycle it? How can it fit into the waste resource streams? What are the regulations like? How can we make people use this? How can it become, something that's attractive from an economical perspective? That sort of thing. I think fundamental scientists are not experts on these issues, and this is really something we will try to improve in WISE, to educate not just the young researchers, but also the senior ones in these perspectives.
Do you have any question from the audience? Raul, I have a question for you. You mentioned that when you're producing things from raw material that are virgin, it's of better quality than if you use recycled material. What we have seen in our way of research is that we can produce a phosphorus that is clean than anything you can contribute on the market today. And that's what we're going to present next week in New York. But also how the city of New York can reduce their costs with several $100 million by implementing a resource thinking for the wastewater treatment plants. So becoming resource plants instead of wastewater treatment plants. So I would love to share that and invite you to our research centers to see that it's possible to create something more of value. When will we see results then from your work? I know that you are starting now in November, because I know that many people here, when I talk with them, they ask, when will we see the standards? When will they come? What will happen now?
Usually it takes 3 years. The documents usually takes 3 years to agree on. That is a problem. Of course, it also means that if we did it faster, we did not have the consensus. Consensus takes time. We have to follow the process. So that is what we should expect. But also during the work, when we do it, the experts that participate there get wiser. It's like a booster to really understand the problems and how to solve them in the standardization work. So I think that anyone participating is really benefiting from it, because you can sit in your islands and you can understand parts of that. But coming back to the first one, you say the quality of the recycled material is better than the one you get from virgin. That is what we want to achieve. So I appreciate that, because what the industry of today is made linear. So that is what we based on virgin material, and we expect that. So it's nice to see that you solve that. That is precisely what we would like to see in circular economy. So,
Bro,
yeah.
You have a good example to speak about in the future then.
Definitely.
Thank you so much.